Hi, I'm Gizem Ölçer and I am an electrical and electronics engineering student at Bilkent University. This is the project presentation of Foundation of Magnetic Resonance Imaging course. This project aims to find out the ways and methods to eliminate ghost artifacts on magnetic resonance imaging. As a brief explanation about ghost artifact, it is shown up in the original magnetic resonance image while it shouldn't exist. Thus, it leads to decrease the quality of image, so it may birth very problematic results on illness detection. This is actually why it is significant to get rid of that problem. We can divide the reason of ghost artifacts by two based on motions. They are physical and periodic movements. Physical one can be occurred because of the movements of patients, since while scanning it can be sometimes hard to stay stable, so those motions can cause unwanted effects we called ghost artifacts. As an example, for periodic movements we can say respiratory movements, bowel movements, swallowing, and also heartbeats. Those motions conclude in ghost artifacts too. Since those effects can be very problematic and serious for illness detection, they should be detected and eliminated. There are several examples of ghost artifacts in figure 1. We can see the ghost artifacts that are illustrated by the arrows. Fortunately, original image is not distributed by the ghost artifacts. They are not intersect, so it doesn't affect the image quality. And the second one is image we see the ghost artifact in phase encoding direction on the abdominal region. At the last one, this image ghost affects repetitive ghost effect, and it gives us two intuitive information about the reason of that. The prediction is breathing while scanning. I've found several solutions which can eliminate those problems. First one of them is iterative inverse problem solving. The second one is reference-free API ghost correction algorithm. The last one is parallel imaging approach. First one is iterative inverse problem solving. This is one of the way that eliminates ghost effects, which are mainly caused by patient's motions. This method is applying after process. It's like an image correction by iterative approaching. There are several steps. Data is obtained by applying a Y gradient by fixing T before the data was acquired. Frequency encoded is used in encoding while data is scanning. Inverse Fourier transform is taken to reconstruct image. This image may include ghost artifacts. After then, the iterative method is implemented to reduce the amount of ghost artifacts. Due to this method implements after the image processing, perfect predefined model on movements should be known by us. As a brief calculations are done for magnetization of the image. After that, we desire that it matches the magnetization of the image that we get. The second one is reference-free API ghost correction algorithm. Purpose of this algorithm is to complete removal of ghost artifacts without pre-scan data. Algorithm is in here. We can see -1 power n term in the equation 1. Sign alterations leads to create odd and even lines, and this is why that Nyquist ghost artifacts appear. Set of two set of k-space creation, and now formed even and odd signals can be declared like that, and then we can get rid of the ghost artifacts. Even and odd signals are subtracted, and this term could be changed in a sign term, like in equation 4. In equation 4, difference between even and odd signal altered into a sign term, but delta fxy is too small to write like that. The difference between odd and even virtual k-space is the Fourier transform of a gradient odd image multiplied with RF offsets. In equation 6, f refers to 2D Fourier transform. Right now we can be able to use this even and odd property to get rid of ghost artifacts. This method is basically based on difference between even and odd virtual k-space data that is a Fourier transform. And third solution is parallel imaging approach. This method way is for a Cartesian sampling scheme. Every voxel CI in coil MRI contains MLI's voxel signal PJ. In that figure, it can be seen that ghost signal of the material that is moving is going from 0, 0. So the intensity of the ghost is to the coil sensitivity at the place of the artifact source. Basically, we can say that original encoded the sensitivity of the artifact. Ghost artifact eliminator process is will be given later. First, make an assumption which CI is not influenced by an artifact. Then this assumption is well to see the signal of coil fit or not with the obtained coil sensitivity before. If any mismatch happens, then we can say it's an artifact and stand for artifact with LAA. Then LAO is identified. This solution has two parts, sense and grappa. Sense aims to collect under sampled K space. This K space is an analyzed image. In order to apply extended sense reconstruction, we have to construct metrics that are coming from the superimposed ghost as unknowns, and grappa works with under sample case space rather than working with analyzed image, which is what sense does. And as a conclusion, due to this is very hard to understand and learn that conceptual topic, I couldn't make any simulation on MATLAB. Most of the time that I spend on the project is donated to the understanding the topic, reasons, and solutions of ghost artifact. Thank you for listening to me.